Hello, chemists. I want to welcome you to one of the most iconic parts of chemistry, which is the mole, our most famous Avogadro's number, and how to use it. I'd like to remind you first to have your periodic table and calculator out, and be ready to pause this video so you can practice your own calculations. And also feel free to speed me up 1¼ 1½ times. I do tend to go slow in parts. First of all, just want to give a real world example on why we use the mole, because it's easier to count in groups. So if we look at this first example, if we have 4½ pounds of nails, and we know that a dozen nails weighs 0.5 pounds, most of us can do mental math there to figure out that we have 9 dozen nails. At 0.5 times 9 will give us 4½ pounds. So just using this analogy, 9 dozen, of course there are 12 nails in a dozen, we're going to get 108 nails. So this is very similar to what we do in moles, except we're using a lot bigger number than a dozen. We're using 6.02 times 10 to the 23rd. It's a very convenient number for counting large numbers of atoms and molecules. So in this next example, maybe a little tougher to do with mental math, but if we have a dozen M&Ms and we weigh them and they're 19.4 grams, we can figure out, well, what if we have a bigger sample? Can we figure out how many M&Ms without actually counting them? So if we had 388.2 grams of similar M&Ms and started there, and then using our dimensional analysis, let's scrape the cobwebs off of that skill. 19.4 grams is 1 dozen. And of course, 1 dozen is going to be 12 M&Ms. So it turns out that 388.2 divided by 19.4 is very, very close to 20. And it's a little bit more actually, but if we take that 20 and multiply by 12, multiply all this out, we get very, very close to 240 M&Ms. And that saves us a lot of time from having to count every single one of those M&Ms. All you need is a scale and to be able to count out a dozen. So imagine doing that with atoms and molecules, which are impossible to count because they're so small. Using the mole is much necessary, much more helpful. So in chemical equations, which was our last unit, we would just say carbon plus oxygen gives carbon dioxide, but it's not practical to do that in a one at a time, 1 atom plus 1 molecule gives 1 molecule. Those are just way too small to even witness those. So from now on, it's better to read this as 1 mole of carbon reacts with 1 mole of oxygen molecules, and that's going to yield 1 mole of carbon dioxide molecules. It's kind of weird because how is it like 1 plus 1 gives 1? Well, we're taking 1 plus 1, but we're combining them into a new thing, so we're making a bigger molecule of carbon dioxide. So a mole of carbon plus a mole of oxygen will make a mole of carbon dioxide. So we know a pair is 2, a dozen is 12. A mole is this number that you'll probably never forget, 6.022 times 10 to the 23rd particles. It could be anything. So hopefully you watched Tyler DeWitt's video. He had some great examples of jelly beans and donuts and how much space they take up if you had a mole of them. We'll have another few examples down below here. So Avogadro's number, also written up here. I'm not going to rewrite it there. 6.02 times 10 to the 23rd particles for every 1 mole. So the molar mass is what's on your periodic table. So if you look at the non-rounded or the bigger numbers on the periodic table, for instance, chlorine is 35.45. So the molar mass is how many grams 1 mole of that element, or if we combine them, how much that molecule weighs. So let's look at some of these examples before, but the molar mass is the mass in grams of 1 mole. And sometimes I'll abbreviate that MOL, it's not much shorter, or sometimes you'll see this 1M with an apostrophe. That apostrophe is important because M means a lot of things in chemistry. So mole, MOL, or 1M apostrophe, they all mean 1 mole. So look at sulfur on your periodic table. You can pause if you want. It weighs 32.07. Our units are grams per mole. And of course, if I had a sample, just like in Dr. DeWitt's video, if I had a sample of 1 mole of sulfur, 32.07 grams, it's going to be very, very close to 6.022 times 10 to the 23rd sulfur atoms. Same goes with carbon. If I had 1 mole of carbon, that could be graphite or diamond, 12.01 grams per 1 mole. Each carbon atom is smaller, so that's why it has less mass, but you still have the same number of carbon atoms. And if you haven't yet, you might be speeding me up to 1.25 or 1.5. For gold, it's a little bit repetitive, but 196.97 grams per mole. And there are also 6.02 times 10 to the 23rd. Might be a little repetitive here. And for uranium, our heaviest naturally occurring element, 238.03. Probably don't have any of that sitting in our classroom. It's a little bit radioactive. But a mole of uranium atoms is still 6.022 times 10 to the 23rd. All right, so what is the mass of 1 mole of iron? Well, we just look at the transition metals in the top middle there. Iron is 55.85 grams per mole. And the average mass of 1 iron atom in grams, we have to do a little bit of calculation. So for 1 single iron atom, we're going to have to divide by Avogadro's number because this is the number of atoms. So we're going to divide by the number of atoms in a mole. So 1 divided by 6.022 times 10 to the 23rd is going to be a very small number. And then we're going to multiply how many grams of iron, which we just said is 55.85 on our periodic table, grams of iron in 1 mole. So I'm going to pause for a second, do this calculation. And I get 9.28 times 10 to the minus 23 grams. That is a very small mass because 1 iron atom is a very small thing. Not much there. So these are kind of fun. How long would it take to spend 1 mole of dollars? I think this is somewhere around 19 million years. I'll go through the math on a couple of these, but if you just think about how to do it, if you spent $1 billion per second, and then we figured out, well, how much is a mole of dollars? So 6.02 times 10 to the 23rd dollars. You would get so if we had a mole of dollars and divided it by 1 billion, you still get a really large number, and it turns out that it would take 19 million years to spend if you were spending $1 billion per second for a mole number of dollars. If you have a mole of pennies and divided it among the almost 8 billion people on Earth, you end up getting $752 billion per person. Now, economics will tell us that that's not going to make everyone rich. It just means that a lot of people would have a lot of paper money or pennies. And as you might imagine, if you had a mole of pieces of paper divided into 1 million equal piles, how high would each pile reach? Very, very high. I think you guys are getting the idea. A mole is an astronomical large number. If you guys want to go through and try this on your own, I'm not going to take the time to do that right now. Probably the most important part of this, though, if you have a mole of water molecules, still a very, very large number, but it's just going to fill up a beaker to 18.02 milliliters. So 18.02 grams of water. That means that each water molecule is incredibly small, and they are all squeezed into that little sample of water, and that same large number of pennies or dollars or sheets of paper or donuts or jelly beans that is like the size of the earth or crazy large numbers is that huge number into that very small amount of space, which is telling us, wow, water molecules are really small. All right, let's get down to the meat of this, which is how to convert between grams and moles and molecules. And if you take one thing out of this lesson, is that moles are at the heart of this. So in order to find out anything, we have to find out the moles of substance. If you're already given moles, then that's pretty easy. You only have one step. But if you're given grams or a number of things, you have to convert through moles. So it's really, really important that we know which direction to go and which conversion to use. So if we're given the grams of a substance, we are going to have to divide by the molar mass from the periodic table of that atom or molecule. So that's if we're going in that direction. If we know the moles and we're converting to grams, that means we need to multiply by the molar mass, again, on the periodic table. Remember, for diatomic elements like oxygen, O2, you would have to double the 16.00 to 32.00 in order to find the molar mass of oxygen. And that's going in this direction. If we know the number of moles and we want to find out how many, the number of particles, not the mass, but the number, then we have to use Avogadro's number. So in this direction, we'd multiply by Avogadro's number. It's given that designation, capital M with a subscript capital A, or in this direction, we would divide by Avogadro's number. So let's do a couple examples, and then of course your homework has a whole bunch of these examples. So how many moles of sulfur are in 255 grams of sulfur? So 255 grams of sulfur, and then we're going to multiply by 1 over the molar mass. 1 mole of sulfur is 32.07 grams. That's right off the periodic table. And then we're done. We just have to type that in our calculator. 255 divided by 32.07. Hopefully you are doing this along with me. And you get 7.95 moles. So almost 8 moles of sulfur. Now if we're trying to find the number of atoms of sulfur, we could start again at 255 or just start with the number of moles because we're already at this spot. So we have just gone from grams to moles. Now we want to go from moles into number of particles. So let's take that 7.95 moles of sulfur. And for every 1 mole, our favorite number, 6.02 times 10 to the 23rd sulfur atoms. And that gives us 4.79 times 10 to the 24th sulfur atoms. Huge number because that is a significant number of moles. So almost 8 moles of sulfur, so we're going to have way more than 1 mole, which is 6.02 times 10 to the 23rd. of sulfur atoms. So this is how a lot of these problems go. We're going to skip 2 and 3 because we don't have our graphite pencil in front of us. You have plenty of these examples on your homework. But I do want to do number 4 because, and number 5, because these are actually a little bit, can be, number 5 especially, is multiple steps. So if we have 12.5 moles of sodium, and sodium weighs on your periodic table, put 1 mole of sodium on the bottom, 22.99 grams on the top. I got 287. And remember, using dimensional analysis, we always want our units to cancel off and make sure our final answer is in the units that were left on top. So this last one's a little tougher because it's a 2-step problem. 3 actually, because we're given pounds of lead and we have to convert that first into grams because our molar masses are in grams per mole, and then convert to moles, and lastly convert from moles to atoms. So 3 steps. We're going to say 18.5 pounds of lead. And you might remember that lead is PB, and that 1 pound is 453.6 grams. It's a conversion that pops up quite a bit. And then, according to our periodic table, lead has a mass of 207.20. Per mole. And again, we're doing these in all one series of dimensional analysis calculations. And then every 1 mole of lead is, of course, 6.02 times 10 to the 23rd lead atoms. I'm going to pause for a second while I do this calculation. And I got 2.44 times 10 to the 25th lead atoms. So if you've ever held a piece of jewelry or a piece of dry ice and you've wondered, well, how many atoms of platinum or gold or silver are in that piece of jewelry, or how many carbon dioxide molecules are in that piece of dry ice or ice cube, we can find it just by weighing it, and we know that they're a pure substance. The last little part we're going to cover here is really important. It's called molecular mass or formula mass, and that is if we're not dealing with a single element. We have to add up all the elements that are in the chemical formula. So molecular mass is the sum of the atoms in what are called atomic mass units. We don't use them very often because we don't have single molecules very often. So the molar mass is the same. That's what we use more, and it's measured in grams per mole. So if we look up benzene on our periodic table, it's C6H6. This is a main component of gasoline. And if we have 6 carbon atoms, so we look up the molar mass of carbon, and then we're going to add that to 6 times hydrogen. So we're going to look up the molar mass or the atomic mass of hydrogen on your periodic table. So you might remember that carbon weighs 12.01, but that's also on your periodic table. 6 times 12.01 grams per mole, plus 6 times 1.01 grams per mole for hydrogen. And if we add all these together, we're going to get 78.12 grams per mole for benzene, C6H6. So it's actually kind of nice. So if it was molecular mass, the only difference between these two is molecular mass would be an AMU, but we don't use that very often. So this one, the molar mass, is what we usually use, molar mass, formula mass. let's just do stuff in grams per mole. It's a very rare occasion where I'd ask you for the molecular mass of just one molecule. So for ionic things, we call it a formula mass because ionic compounds actually don't have molecules. They're all one large clump of ions. So if we say, let's find the formula mass of aluminum sulfite, again, this will be an AMU, our lesser used unit. And then the molar mass will be in grams per mole. But I'm going to pause and let you find aluminum sulfite. Of course, you have to write the formula correctly. And then I'll pause while you find this formula mass. Hopefully for the formula of aluminum sulfite, you got Al2SO33. Aluminum has a +3 charge. Sulfite has a -2 charge. So that's our formula. And for the formula mass, 294.17 AMU, and the molar mass in grams per mole, which we use way more often, is 294.17 grams per mole. So like I said, 99% of the time, we're just going to find things in terms of moles. So 294.17, if we were holding 1 mole of aluminum sulfite, it would weigh 294.17 grams. Lastly, let's do number 3 here. So this is just a little bit bigger formula. We would add up all the atoms and find the molar mass of TNT, sulfuric acid, same thing, H2SO4, add those up. We have multiple examples on our homework of this. But I do want to do number 3 as our last example. How many molecules are there in a piece of ice with a mass of 4.65 grams? So if you want to pause this and do it on your own, or if you just want to have me on in the background, I'd like you to go through this on your own. So ice, of course, is water frozen, 4.65 grams of H2O. And then we're going to say for every 18.02 grams. Well, how did I get 18.02 grams? Well, there are 2 hydrogens, which each weigh 1.01 gram per mole. And then there's 1 oxygen, which is 16 grams per mole. And if I add all that together, I end up getting 18.02 grams per mole. So that's how I got 18.02 grams. That's for just 1 mole of water, 6.02 times 10 to the 23rd of those. So our next step, of course, is going to be converting from moles of water molecules into the number of water molecules. And we get 1.55 times 10 to the 23rd. Hopefully this introduction helps you guys get started with your mole conversions. And thank you very much.